The solar window for water collection and purification investigates building scale, point of use, water treatment, and reuse. The student team is led by Anna Dyson of the Yale Center for Ecosystems and Architecture and Jae-Hong Kim from Yale Chemical and Environmental Engineering. Globally, and with increased urban density, we need to better manage how we use environmental resources to meet our basic human needs. Centralized urban water management is costly and lacks resilience. We need to ensure safe drinking water that doesn't burden the environment with chemical and energy-intensive processes. We need to maximize the potential of solar energy by harnessing it for point-of-use application, to reduce dependence on fossil fuels, and to foster resilience through networked decentralized systems. Solar water disinfection is a low-cost, readily available method for point-of-use water treatment. Through UV and thermal effects, it is reasonably effective with bacteria and parasites, but protection against certain waterborne viruses may require up to 30 hours of sunlight to ensure full inactivation. We are seeking to overcome the current limitations of household solar water disinfection technologies, reducing the length of time required to treat the water, improving the volume of treated water per day, and providing a robust and reusable system that would ensure consistent water safety. This project directly addresses the water energy nexus in buildings. Buildings consume over 40% of energy globally. Of this, domestic water heating accounts for up to 25% of a household's energy costs, but less than 1% of US households own solar water heaters, nor do we really see adoption of domestic water capture and reuse. On-site water and energy management is essential to meeting global sustainability goals. We need to increase the efficiency of building systems. We need to better harness the abundance of solar energy in buildings. We need to better manage how water and energy is consumed and produced. And we need to find affordable means of meeting these household needs sustainably. This research area incorporates novel methods for water management in building envelopes. As a building integrated strategy, we propose combining essential needs in buildings as an integrated system. The concept takes the form of a window and could be viably shaped as structural load-bearing glass blocks that are customized for capturing solar energy by climate type. The glass geometry concentrates direct solar rays on fluid passageways for water treatment and heating, and in doing so, converts unwanted solar heat gain for functional purposes, while allowing diffuse light through for daylighting and views, cumulatively reducing building energy consumption. To enhance conventional sodas, researchers at Yale have been investigating the use of visible spectrum photosensitizers that amplify the generation of reactive oxygen species under sunlight at low additional cost. Experimental results and predictions based on global solar irradiance data suggest that over 99.99% of inactivation could be achieved within 5 minutes in the majority of developing countries, reducing the time for sodas by 2 orders of magnitude. We tested engineering prototypes which incorporated the plant dye-enhanced sodas in flow-through configurations scaled to the constraints of a typical window, assessing operational and environmental criteria as well as scalability. Based on preliminary testing and the goals of the project, we have identified the design criteria that would support a multifunctional system design, combining solar energy collection and water disinfection with architectural requirements such as transparency to outside views, reduction of solar glare, heat gain, the modulation of daylighting, and reduction in lighting energy loads. We are currently investigating how concentrating solar components, which, through increasing photo density on the fluid passageway, could further enhance the effectiveness of biorenewable-based water treatment processes for vertical facades across wider geographic applications beyond the direct solar climates. Lab-scale assessments will be completed and compared with the testing of a window prototype under daylight conditions to evaluate building scale performance. The project aims to be easy to deploy for widespread uptake by resource-constrained US communities and households who face increasing issues of water and energy security. Imagined as a window that meets the functional needs of a household, increases its flexibility and affordability. A family would benefit from a solar window that gives visual indication of when the water is safe to drink, promoting prosperity by reducing waterborne disease burdens. Herein, renewable energy for cleaner, decentralized infrastructures reduces the burden on natural ecosystems, protecting the planet and rounding out the P3 approach to our work in urban energy and water. Thank you.